Thank you. So I will sort of push this a bit further and discuss basically how in practice do we compute these correlations, what are the issues, and how all these bias coefficients could be like measured relatively easily from numerical simulations. So what we usually do is that we take like a sort of local bias approach, and we write down like a halo of a density, and we expand it in series as a function of the mass of a density smoothed on some suitable scale R, and then the bias coefficients are the Taylor coefficients of these series expansions. So in this calculation, when you start with this model and then start computing correlators, there are two issues. The first of them is which smoothing scale you should take in these calculations, basically what is the meaning of this delta H. And then if you, for instance, compute like the 2-point halo correlation, you get basically already at linear order like an infinite number of loop corrections because of the way this series expansion was written down. So this actually second issue can be fixed in two ways. The first possibility would be to say that what you're actually measuring from the simulation is this whole parenthesis here, and so that the biases that enter this series expansion are only bare bias parameters. And this procedure is known as renormalization of the bias and was pioneered by Mike Donald. Another way would basically be to just redefine what exactly you mean by delta R to the power n, right? And so actually there is a nice way to do that, which actually goes back to a work by Alex Zale from 1988. Since we know that the initial conditions are essentially Gaussian, right, to a very high level, what you can do is basically do an expansion in Hermite polynomials, which is appropriate to the Gaussian distribution of delta. So in this case, basically what you should do is that you should go back to your local bias expansions and replace these powers of delta R with Hermite polynomials of the nth degree, right? But you haven't answered the question. So, but what is R in this problem, right? So it's clear that, the measurements, that the way we do them from simulations, we are basically counting pairs. We are not doing any counts in sets, so there is no R in the problem to some extent. But if you have to push this further, you would say, well, here there is an issue because we see a feature in the matter correlation, which is the baryon acoustic oscillation. So this feature is localized. It's centered at 100 megaparsec co-moving separation, but it has like a finite width of the order of 20 megaparsec. Now, if I had to interpret this delta H here as a counting cell density, what I should do is that I should take R really very, very large so that I have so many halos within each cell that I can really treat all this as a continuous field, which is the way that things seems to look like here. But if I would do that, I would completely smooth out the feature. So then you say, well, you cannot do this, right? So then if you don't want to smooth out the feature, you should take basically R to some extent of the order of megaparsec or less, right? But then, okay, you won't have like more than maybe a halo per cell, right? So where is the continuous field? So basically the correct answer, I think the only natural scale that enters the problem is the halo mass scale, and so you should basically take just this halo mass scale as the smoothing scale. So then the consequence is that, of course, you cannot interpret the delta H as a counting cell density. It's basically just like some sort of mean field quantity, right? It's given a certain realization of delta in the simulation, what's the most probable halo density field that I get, and that's the answer. Well, sorry, previous slide. That's the answer, right? But it's not. It's definitely not something that you will measure. Okay. So this being said, how do we generalize this? Well, to basically pick. We have heard from Ravi that there are many variables. Well, I think it's very clear, right? We have many variables, and we need to assign to each of these variables like a suitable polynomial, right? So let's go back to these pick constraints. So what is the selection function in the initial condition? The selection function basically depends on the density field and its first two derivatives, right? Because we need to specify where are the peaks. So we have a constraint on the first derivatives, and then we want the density profile to be, I never remember if it's concave or convex. I think it's concave. And so we need also to know what the second derivatives are doing. So from all these variables, because this delta H is invariant at the rotation, I can construct basically six invariants, right? So the first, nu is the peak height. Then u is the curvature, basically around the peak. This eta squared is basically the gradient squared, right? And then I have two additional invariants that come from the second derivatives, which I call J2 and J3, and they are basically related to the traceless part of the matrix of second derivatives. And so then you can actually show the following, and it's some work in progress, but you can show that you can compute all these peak correlation from like a bias expansion that generalizes the local bias approach. In this case, everything is local because the constraints are just specified in terms of delta and derivatives, but you could, of course, imagine constraints in the initial conditions that basically are imposed on the second derivative of phi, for instance, gravitational potential, in the case where you have, for instance, ellipsoidal collapse. But so that's basically how the how the things look like. So you basically have like a series, perturbative series expansion with bias parameters, right? So in this case, there are basically, I don't think I missed, did I miss something? I said 6 variables, and I have 5 indices. Sorry. Okay, maybe I missed something somewhere. 1, 2, whatever. Okay, I will make the count later, but that's approximately this, right? So these biases, you can show that they're basically ensemble average of these orthogonal polynomials at basically one point, so at a given location. And then each of these biases multiplies basically product of these orthogonal polynomials. So you can see that basically the peak and the curvature correlate, so they go into bivariate Hermite polynomials. But of course, you could just redefine these two variables to have a product of two univariate Hermite polynomials. Then you have this grad delta squared, which is on its own because it's chi-square distributed with 3 degrees of freedom. It must go with the Laguerre polynomials with 3 degrees of freedom. And then you have these two variables, J2 and J3, that turns out to be correlated. Why? Because actually J3, when you look at J3, it can take positive or negative values, but in absolute value, it can never be larger than J2 to the third half. So it's correlated. The two are correlated, so you have like a spatial polynomial which you actually need to work out. J2 would be the shear relative to delta, right? Okay, here there is no gravitational potential. I'm just assuming spherical collapse for simplicity, right? But you can generalize this now, it's obvious. Okay, so why do we care about these terms? Well, we already heard from Ravi that there are a number of effects that we see in simulation, so let me just show you. So B01 here is one of these bias parameters. It's basically a first order bias parameter that has to do with the curvature, U. Okay, so it's the second derivative of delta. Why do I care about the second derivative at large scales? I would say if you have a power power spectrum, you don't care about the derivative at large scales, right? But it turns out that you have a feature in the power spectrum, right? You have the BAO. So around the BAO, the second derivative vary very rapidly, so it has an effect, right? And so if, so this is a measurement, okay, of the correlation function of what we call proto-halos. As you understood, these proto-halos are halos traced back to the initial condition because all what I'm telling you is in Lagrangian space, okay, for simplicity again. All right, so this is the correlation that we measure in the initial condition. The dashed line is the prediction that you get if you only have a dependence on delta, okay? You see, you really fell short of reproducing what we see here. And that's in black, the peak prediction. So this peak prediction includes this additional k-square dependent term at linear order, and it amplifies the contrast around the BAO because of this second derivative of the feature, and you actually turn out to get something which looks pretty close to the measurement. If I go to second order and higher orders, for instance, I have this J2 and J3. What do they mean? Well, they are related actually to the anisotropy of the density profile around the halo. This is a plot from BBKS actually showing you how isotropic or anisotropic is the density profile around the peak. So here you have actually the ellipticity, and here you have the prolateness. And then as you go from here to there, you go basically from low mass halos to more massive halos. So more massive halos tend to be fairly spherical, right? So we expect that the effect of J2, J3 should be small. But as you go to lower and lower mass halos, you have more and more ellipticity and prolateness. So we should expect to have a bias also from this. And so you can actually work out a prediction because once you know how to do these things, basically all the bias coefficients are predictable, right? You just have to crank up the code, right, and get numbers. And so here is basically the bias that goes with J2 at linear order, for instance. Well, it's a second order, sorry, it's a second order bias, but first order in J2. So as you go to very large peak height, so massive halos, there is no effect. You go to 0, random. As you go away, so you go to lower mass halos, you start seeing a bias. Exactly. So here the assumption is that it's all spherical collapse, but absolutely. In reality, the collapse is aspherical, and so they will correlate with the shear, absolutely. So yeah.
And so you might think that the bias factors that go with delta and derivatives of delta
Yeah.
don't correlate with J2.
Yeah.
And so I don't know if it's nicer notation to keep them separate.
Yeah, so I mean, well, I'm not fully satisfied with the notation, but I mean.
Just from the point of view, I guess it's a detail, but I think it's important.
Okay, let me now say one word about all these things. There is also the fact that actually, well, from all these variables, you will get all kind of assembly bias, right? So there is, of course, the peak curvature, which you actually looked at, Neil. But you could also think of the asphericity, J2, J3. Maybe, we will select halos that have, like bias values of J2 or J3. You could imagine the same for the shear, right? What all these things will do, I don't know. But that's probably a good question to ask. In any case, let's move to the measurements. So how do I measure this, actually all these bias factors, right? So the theory, basically, once you specify a constraint, basically where do you collapse from in initial conditions, you have predictions for all of them, right? The question is, do you want to compare this with your simulation? So how can you estimate them? Well, basically, it's very simple, because these biases, they are actually 1 point average of this orthogonal polynomial. So the only thing you have to do, you have to go to your initial condition, okay, because that's Lagrangian, and then you basically average these product of polynomials at the position of the halos, and you get a prediction. You get a measurement of these bias factors. So I will show you only one result, because we will hear a lot about the usual B's, B1, B2, B3, so we know how to do that. The question is, could I also measure the biases that multiplies k-dependent term? So the answer is yes. One more point. There is something that I forgot to tell you here. I put L. How will I do the measurement? Actually, I have to select a scale to do the measurement on. But I don't have to select the halo mass scale to do the measurement. I could select actually any scale. I put L because usually we think of this as, we have this peak background split in mind, and so we think that we should take a very long scale, a wavelength much larger than the halo mass scale. But in fact, you can take any scale. I mean, as long as actually it is different than the halo mass scale, the actual halo mass scale does not matter. So you do a measurement, okay, of these polynomials acting on the smooth field, smooth at that scale, and then you basically, using the fact that there is a correlation between the two scales, the scale where you do the measurement on and the scale of the halo, you can actually extract these bias parameters. And so this is something which we try to do, for instance, for the bias that multiplies gradient squared. Okay, so how does this look like? So here I have the bias as a function of halo mass. So these terms in your power spectrum, it multiplies the k1 scalar k2. Okay, so if you had random field points, if the halos would absolutely not care about this, it would be exactly 0. If the halos were exactly peaks, then you can show that it should be exactly minus 1.5. That's the measurement. The measurement, we did it from two different box size. One large box has 1.5 gigaparsec, and the other one is only 1/6 of this. So, well, the first thing to say is that there is a bias, okay? It's not, it depends on grad delta squared. The clustering of halos in the initial condition, at least, depends on this grad delta squared. Then there is clearly an offset between the two measurements. But I think the reason why there is this offset is the following, is that when we basically compute the correlations between the two scales to extract the value of the bias parameters, we integrate wave numbers out to infinity. But in fact, when you set up the initial simulations, when you set up the initial conditions, there is a Nyquist frequency beyond which there is actually no power. But we didn't take that into account. But I think that the fact that this Nyquist frequency is different by a factor of 6, right? That the K Nyquist here is basically much larger than the other one. I think that if you take this into account, hopefully you would correct for that offset. But okay, what do we learn from that? There is a bias, but it's not exactly the bias predicted by peaks, right? It seems that it will only be the case for the most massive objects. And of course, it's expected, right? You expect that massive halos, cluster of galaxies, they will really be, I mean, their center of mass position will be fairly close to an initial density peak. But as we go to lower and lower mass halos, that will be less and less the case. And that's what we see here. So then you could say, okay, could I, to some extent, at first order, I would say, there is probably or very likely an offset, right? Some scatter between the center of mass position of the halo and the position of the peak. If I do account for this scatter, what do I get? Well, you know, once I had like 3 parameters, of course, I can always get a curve going through data points, right? But I would say what's the real, I mean, what needs to be done next, it's fairly clear, right? We need to go beyond spherical collapse. I think that in principle, I don't see any reason why you could not implement like ellipsoidal collapse in this approach, right? It's just that the constraints will be more sophisticated. But I guess there will be a number of issues, and also one of them is the filtering. What exactly do we mean by this filtering? Is this expected to evolve with time? And also the question, of course, of the baryons at the end. I mean, the simplest thing would be like to have a predictions for pure dark matter halos, and then you paint the galaxies onto that, but it's not completely clear to me that the baryons will not also affect the collapse itself. But, you know, I will stop here. Yeah, what, 70%?
Oh, for high mass, definitely.
Yeah.
For low mass, I thought also it was still pretty good. 70%.
Yeah, but I mean, here you see, because.
Okay.
But here, I mean, it's extremely sensitive, right? You already, you know, you have a gradient delta squared, right? So you're very sensitive to the small scales, what they are exactly doing. So it's enough that you're a bit off. You're not exactly at the peak position, and this will all go up quite quickly. Yeah. But in principle, you could, I mean, you could do this projection for all, you could really do that for all the bias parameters, extract them, and then you come up with your model and you see if it works. Alternatively, you fit, right? But I mean, you will fit at this level, right? I would say rather than fitting a mass function, you fit at this level to some extent. That's true, yeah. But I mean, here again, I think there is some issue with the comparison. We didn't take into account. Another possibility would be that there are other variables that cross-correlate with this one. Okay, in which case you have to be very careful when you extract the value. Because here I'm assuming that nothing correlates with this grad delta squared, okay? So what I measure is only coming from grad delta squared, but as Ravi said, when you're measuring this thing, actually you're measuring like weighted versions of all these k-dependent factors at a given order, all right? And so you have to be careful when you extract. Yeah, but so that's this velocity bias that you were talking about, no? Because in the initial conditions, you cannot have a dependence on grad phi. No?
Well, but one of the previous speakers had something that they call the shift in their bias.
Tobias. So today I will talk about this work that I started with Vincent, Alex Kayagas, Tony Riotto, and Davide Racco in Geneva. It's something pretty new, so comments are welcome. The idea here is to try to write an evolution equation for halos, other than the one we have already. So I will start stating the obvious. So halos are specific regions of underlying dark matter field. This we agree. They are these regions that go over a certain density, so that they decouple from the expansion and start to collapse. And the fact that these regions are particular regions of the dark matter field gives this statistical this bias between the statistical distribution of halos and the statistical distribution of dark matter field. If it wasn't like this, we wouldn't have this workshop. And for this reason, if I want somehow to follow the evolution of halos over time, I should expect that the equation of this evolution should be somehow different than the one of dark matter, just because I'm studying the statistics on a statistical level, because I'm studying the statistics of specific regions of this underlying dark matter field. And so in the couple-Fourier approximation for the coevolution of halos and dark matter, what we do is basically to take proto-halos in the initial dark matter field, identify proto-halos, assume that these proto-halos will end up in halos, and as we were saying, this is yes, exactly. No, it's not an assumption. Yeah, and yeah, and follow the center of mass of these proto-halos over time. So inside the proto-halos, things will happen, merging and so on. But the number density of proto-halos ending up in halos will be conserved. So in general, we could think of define evolution equation for halos as well as we do for dark matter. And the two fluids will be coupled through the fact that the general the Poisson equation is sourced by the whole dark matter field, also for halos. So, but let's take a step back.
So why is the number conserved?
So we assume that this is the assumption. We assume that the proto-halo. Yes. This will work for a certain range of, which work well for a certain mass of range of masses.
Sure. So for a cluster size halos, sure.
Yeah, this is a general treatment. We are not going through the details of the
Halo mergers.
Yes, but
Sure, yeah. You're right to be worried if the little guy, when you trace him back, splits up into lots of pieces.
yes, exactly.
And that doesn't usually happen, maybe for the 30%.
Yeah, so that's why I say for a range of that's why I say for a certain range of masses, this is a good approximation. But as you go at lower masses, there will be.
Still can identify the particle that's closest to the center of your point halo, then you just deal with that. Then that's fine. Then it's just one particle.
Yeah. Well. Yeah. Yeah. Well, in this treatment, basically we are identifying. Yeah. We are following the center of mass. So, yeah. Okay. But this is the treatment that we are doing when we are using this set of equations. And the fluid equation usually come from a collisionless Boltzmann equation. Okay, so we just take a set of particles. Here I will take that have the same mass equal to 1, just for simplicity. And we take a set of particles which are collisionless and interact only through gravity. And in a sense, this is like this is like taking an ensemble average over different realization of the universe. So we can imagine that we have a single particle phase space density. So we have a delta function for each position and velocity of particles. So this is one realization of the universe. Then we take another realization of the universe and another and another. This is like running different n-body simulations. And locally, we can average this different realization and get a macro state, which is our ensemble average phase space density for the number density of particles. So basically, F will represent the probability, the number density at X of particles. And we can try to think, so keeping this idea of halos tracing back to proto-halos, we can think of doing the same thing for halos, right? Because so if this is true, so halos, we can just follow the center of mass from late time to early time and identify these halos as points and follow these points. And in a way, we can do something similar for like a halo ensemble of points. And if we think of doing this, the equation, the collisionless Boltzmann equation will look completely similar. Where now basically we have a certain probability of finding a halo in X, so the number density of halos in X. And now again we take the gravitational field to be sourced by the whole dark matter field. Okay, but here now these R positions will indicate halos basically. So why did I take this step back and got the same thing that we had before? Well, because now we can think of, so how do I insert the information that I'm following halos and non-general dark matter particles? Okay, and this was already actually introduced by Ravi and Vincent. So the idea is to identify peaks of the early distribution of dark matter by saying that they had to have some density overcoming a certain height, okay, without specifying too much the amplitude of this height, and we'll take the most important, I think the most important condition, which is to have a gradient of delta equal to 0. In principle, I could take also the Hessian to be negative and so on, but we will identify halos by these two conditions. And so where do I put now this information? So one idea could be to say, so how do I expect the fact that the gravitational force is acting on halos and on the whole dark matter field? I could try to impose this peak constraint, okay, to the force, and I can do it by, for example, looking at the statistics of this grad phi by studying the mean and the covariance of grad phi. So if I go at early times, grad phi is still a Gaussian variable. I can use these formulas, okay, for computing conditional probabilities. So I will just compute the probability of grad phi being on a peak with these two conditions. And if I do the mean, so I can show that at early times when grad phi is still Gaussian, it will couple only with grad delta, not with delta. And we find that grad phi condition on the peak is proportional to grad delta, which on the peak is 0. And this we had to recover, because otherwise this would mean that halo by halo, they feel a different force than the dark matter, which wouldn't make much sense. But on a statistical level, so when we go to the covariance, we find a different covariance, and this difference goes like moment sigma 0 fourth over sigma 1 square, and means that peaks feel a statistical force given by the fact that we are selecting region, or better here, points of the dark matter field. And so we now can define an effective gravitational force, including this different covariance. So we just say let's define an effective force such that our covariance of the grad phi on the peak is equal to the covariance of this effective gravitational force. And we include this effect in this Boltzmann equation. So we have an effective way of including the statistical force felt by halos in the equation. So everything I said up to here is nothing really new. Actually, we discovered hot water, as we would say, in the sense that this effect is what Ravi was talking about. So and was found 30 years ago, in the sense that because at linear level the effective force is nothing more than the velocity the velocity. So when we look at velocities on the peak, we have a conditional probability, and the halo velocity dispersion is suppressed by some factor, which turns out magically to be the same that we find here when you change things that you have to change. And this velocity bias, you can find it taking a gradient of the gravitational force. So we get a modified Poisson equation, which gives this velocity bias. Okay, this velocity bias it's there at linear level, and this prediction is different from the prediction that I would get when I would look for a velocity bias in the treatment that I showed at the beginning with the coupled fluid approximation, because in that case, even having an initial velocity bias, it will be suppressed by the growth factor. And actually, Ravi already showed. I showed the other plot of the paper where this is. So here there is no redshift dependent. They just in this plot they show the measurement at initial condition at redshift 99. And the points are the measurements. The solid line is the prediction including the velocity bias, and the dashed dotted line is the prediction not including it, and the suppression is just given by the window function. So now what is new of this? So the thing is that with conditional probabilities we can think of relaxing the fact that we only consider grad phi in the initial condition when it's still Gaussian, and try to compute these conditional probabilities at second order. So there is some technique to do it, but it's just technical details. So, but the point is that we will basically find other terms by allowing grad phi to have some nonlinear evolution, and in some way we can do it perturbatively. We did the next to leading order. We find some other other contribution to the force, and this is the effect. So we calculate the covariance with this at second order, and then we find the effective force that can explain this covariance. So just to sum up, and I think I can get the chocolate, right? So, okay, hot chocolate would be appropriate. Okay, so just to sum up, so a statistically biased gravitational force felt by halos. We found this, which generates a statistical bias already at the linear level, the peculiar velocity of virialized halos. And this statistical bias comes into play when we want to compute statistical quantities. I said statistical like 100 times. I guess you got the point. That this is important when we compute power spectra, trace spectra, and so on. And we introduce this effective Halo-Boltzmann equation to try to see what happens to this effect when as evolution goes on. And yeah, so the question is now: so are we able to see this effect at late time? So there are already some measurements. The effect, as we already saw, gets a bit polluted by other things. But so to have a theoretical treatment of this, what this effective Halo-Boltzmann equation could be a first attempt.